Hi, folks. My name is Jamie Kostelnik. Thank you for tuning into the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Matt Thomas and Stephen Slaughter. For those of you who are new to the meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone video system. We will wait until the end of the presentation to take questions. In the meantime, please do your best to make sure your microphone is muted when you aren't intending to speak. Okay, now I'll introduce today's speakers. Catherine Pennington is an engineering geologist specializing in landslides and coasts at the British Geological Survey. Her main interests lie in interdisciplinary working to capture landslides as they happen, be that via monitored landslide field observations or real-time global scale data analysis of publicly available data. She is also interested in science communication and co-development to empower communities and hazard management. Roxana Chuan is a geohazard scientist at the British Geological Survey. She has a background in environmental geological engineering and geohazards and a track record in landslides vulnerability assessment and multi-hazard risk research. Her main research interests lie in better understanding the risks and impacts associated with interacting natural hazards and disaster risk resilience. So Roxana and Catherine, whenever you're ready.
Hi, thank you very much for the intro, and thank you for inviting us to come and talk today. We're absolutely delighted to be here. So let's do the screen share. It wasn't playing ball earlier. Fingers crossed it will work.
It looks good on our end.
Doesn't on mine. Hang on. There we go. Right. Yes, right. Okay, good. It's done it. So stability in motion. So we're going to give an overview of the research that we have been carrying out at BGS, what we've been carrying out a little bit in the past, what we're currently doing, and what we're hoping to do in the future. And to do that, there we go. We want to take you on a journey through scale, spatial scale. So this might be starting at the local scale, looking at monitored sites, through to the national scale and regional scale, by which I mean within. So sometimes people refer to regional as in continental scale, sometimes people refer to sub-national. So this is talking about sub-national or county level, as we would have here. Up into the continental scale, and then finally into the global scale. But before we start to talk about landslides, I thought I'd give you a brief introduction into who we are, BGS. So we are the oldest geological survey in the world. We began in 1835, which makes us 189 years old. We're focused on public good science for government and research to understand Earth and environmental processes, and we are the UK's premier provider of objective and authoritative geoscientific data, information and knowledge, with the aim of helping society to use natural resources responsibly, manage environmental change, and also to be resilient to environmental hazards. We have an annual turnover of about 55 million a year, of which around 50% is from government funding and around 50% is commissioned research. And this roughly 50-50 business model means that we're doing science research, but we're also working in the commercial environment, so we provide services and gain an income from this as well. I should also mention on that previous slide that as part of the core values, our impartiality element is one of the most important parts of the work that we do, in that we need to be able to provide objective advice to the stakeholders. So this organisational overview shows how our work is divided up into different strategic pillars, as they've been called, and then the work of our area in landslides sits mostly within the living with geological hazard science priority, but also covers nearly all of the other elements as well. But we're particularly looking at helping society be resilient to geological hazards, both in the UK context and internationally, with lots of different partnerships and stakeholders. So in terms of that living with geological hazards, as we've divided up, the organisation's divided up. So landslides as a team, we don't just work in a landslide silo. So we are working in amongst others, looking at lots of different ways of detecting change. So we have what we're sort of called the 3 Gs, but nearly into the 4 Gs, which is so geodetic. Can't see my cursor. No, so the bottom left corner of that triangle, so geodetic detection of change. The top one looking at the geotechnical element of that, and then the right hand side, bottom right hand side, is the geophysical and environmental monitoring. But we also have geosocial sensors as well, all wrapped up into that. So the way that we do that is we map and we monitor. We characterise and understand better the different processes at work. We do this through delivery of products and services for our stakeholders, and we're analysing risk and evaluation of vulnerability and exposure. We're also developing innovative technologies, enhanced sensors, networks, analytical tools and tailored platforms. And then we also work to communicate these strategies to influence community response to natural hazards. So this is both inland and at the coast. So I just thought I'd show our shiny happy faces. So this is our team within our landslides team area, mostly made up of a combination of engineering and geohazards scientists, but with other expertise as well. But as I said before, we're not just working in just our group only. We have access to more or less every other kind of geological expertise that we have at BGS. We also were awarded at the World Landslide Forum World Centre of Excellence in Landslide Disaster Risk Reduction. So that's a nice thing to be recognised to have. So turning to our landslides research, we've tried to divide this into themes to try and get the message across. So we're starting at the left, so we're looking at monitoring and data acquisition at local, national, regional, global scales. Then we're looking at our maps and our models, forecasts, and the way that we respond and provide advice and communication. Underpinning all of this is our national landslide database once we're looking at UK work, and our expertise also UK and international. So before we start getting into the local scale element of things, I just thought I'd quickly touch on our national landslide database, because that is the underpinning data set that we have for the UK. So it's currently got about 18,500 records in it. They come from a real wide range of information sources. So it might be our geological maps, or it might be PhDs, or it might be other databases that people have done, or it might be commercial work. But more recently, it's been social media data, and I'll come back to that later. It's currently the best resource for landslides information in Great Britain. So we don't currently incorporate within the data set, for lots of political reasons, Northern Ireland. Our Northern Ireland counterparts have their own databases, but coming soon there will be an amalgamation of the two, hopefully. It's openly available, index level data openly available on our online GIS, the GeoIndex, and where you can get information sort of about where it is and where the landslide is and the approximate date that it happened, or it might be to within a day, and then bibliographic references to find out more. But deeper in the database, we have more information about the location, something more about the slope, what the style and the type of landslide, when it happened, what caused it, the impacts that happened, any additional information, and then these bibliographic references or photographs. And this is updated on a daily basis continually, 365. So at the local scale, we have several landslide observatories. One of these is on our North Yorkshire coast, near a small village called Aldborough, and we've been working here since about 2001. What we've got is several boreholes that are in parallel pairs with piezometers and inclinometers. We've also been through the whole range of LiDAR equipment, going back from the very old what was called the nodding donkey that took forever to capture very small amounts of information, to now roving backpacks, and now LiDAR by drone, which means we can cover much quicker, wider areas. So here, not only are we looking at the processes going on within the cliff, we are also looking at how the beach and the cliff interact and influence each other. One of the other sites that we have up in the same county area is Holland Hill, which is the top right-hand images. This is where we've been testing, again, lots of equipment and different methodologies, but in particular geophysics, through a prime system, which is essentially looking at how moisture moves through slope using ERT methods. As well as this, more recent work has been looking at using the Internet of Things. So if you're not already aware of the Internet of Things, this is essentially a system which is autonomous in the sense that you can set particular thresholds for which point a sensor would make its own decision and take an action based on information it's receiving. So we've been developing these with Bournemouth University and Dorset Council on our south coast, and where we get some nice rock falls. This has been through two projects. One has been this 5G Rural Dorset project, which is now finished, and that was really more about understanding the networking end of this. And now we're working under a new project called the HUT, which is an EU Horizon project where we are placing more sensors on the cliff and trying to develop our dashboard where we're getting real-time information. So at the moment, we're looking at answering some science questions around the influence of thermal change over rockfalls, be that at the cold end or the heat wave end of the weather, but we're also looking at longer term across that whole county, looking at climate and how that is influencing change. We also have been working for quite a few years with many, several different universities, but in particular Edinburgh University in the granular flow dynamics group, where we've been using their flumes to test various different tests about how material moves down slopes. And since then, we've developed a prototype, a small flume in our landslides lab, where we've been looking at trying to simulate granular flow to calibrate the Montevecchio landslide, where they have, with the University of Bologna, where they have a post with the camera on, and then you see the material moving down slope past it, and we're trying to work out, is that real movement that we're measuring, or does it need calibration? So that work is currently being written up at the moment. We also have engineering geology labs to back up the geotechnical information. So we've got rock and triaxial testing and shear box, etc., as well as resistivity testing equipment with dew point. And that's been mostly to do with calibration for the prime system that I mentioned earlier. And a lot of this information then goes into a national geotechnical properties database, which is that top right image, and as well as the stuff that we've collected in and tested ourselves, that also includes work from other ground investigations. So moving towards automatic landslide detection. So one of our colleagues here, Alessandro Novellino, has been building the landslide tracker with others as well. So this is about addressing data latency in the sense of trying to get information about where landslides have happened, particularly during multiple landslide events where there may have been a severe weather event or an earthquake, for example, and lots of landslides have all happened within a region. So this is using convolutional neural networks to automatically generate maps of landslides. So we've tested this in small areas in Scotland and then across a larger region in New Zealand, looking at the February 22 landslides, and that creating a heat map of those was the easiest way of displaying those. This currently, well, at the time of doing that work, it was over predicting where the landslides were. So there's been some more work done recently on that to refine it. And then we've also been using the, did you want to talk about to this one actually?
Yeah, I'm happy to, yes. So part of the work we're doing on automatic landslide detection is really to try to apply existing services, existing providers of platforms, particularly in Europe, the Earth observation facilities that are provided through the European Ground Motion Sensing Service, which actually allow us to predict ground movement in time, particularly across large regions, continental scale. And the way we're doing that is actually through a research application currently that looks at how we can use Earth observation for multi-hazard science, where we try to assess the seasonality, strength, and trend behavior associated with ground movement due to subsidence as a result of compounding heat waves and droughts. And we have a case study located in southeastern part of the UK, where we're trying to identify environmental indicators, preconditioners really of potential movement over days, weeks, or seasonal timescales. So this research is really embedded into a wider research objective, which is aiming to identify what are the relationships or interdependencies between hazards such as heat waves, droughts, and their manifestation on the ground, either through subsidence, rockfalls, heave, or other types of such processes, and how these interactions result in impacts on the ground, either on current infrastructure, critical infrastructure, or water reservoirs and vegetation health or crop loss, for example.
Thank you. So that's at the moment on the continental scale. Moving up from that and starting to look at more global scale, then we start to need to look at slightly different information here. So we've been focusing a lot on using social media to get information on a daily basis, but we do have different ways of getting information from the public. So one is from a UK perspective, I should say. One is a form that the public fill in and submit, which is that bottom form. But perhaps the most useful information has been over the last must be 12 years now, has been coming from Twitter. So we have an account on there where we use this every day to look for information about landslides reported in the UK. And we're also on Blue Sky, but this is still quite early days in that. And then the kinds of information that we can get from that are things around the type of landslide, the impacts, what's caused the landslide, and of course the timing. And because everybody's got smartphones now, there's always cameras, and then more recently we've had a lot of drone footage as well. But this graph shows the influence that we've seen in the data that's become available to us since we started doing this in 2012. And during the peaks, it's at least 10 times more than we would have had before. There are, of course, lots of interesting points to think about when it comes to data bias, as well as ethics around this. So, but that's for another talk entirely, really. So taking that work further on from just the manual searching. So I work with others at the Qatari Computer Research Institute and the European Mediterranean Seismological Centre to build a tool called the Global Landslide Detector. This is essentially looking for keywords around landslides in 32 languages. And then we built a machine learning model that can identify landslides in photographs to quite good success. So it sucks the data in using the word sentiment analysis, and then it classifies landslides and not landslides, puts all the landslides that it thinks are a landslide on the web page, and then places them on the global map. And this was all going very well until the recent changes and challenges at Twitter. So things have become a little bit less effective since then. However, our maps and models, so I just wanted to show this partly so that you can see the interesting outfits worn in the field a long time ago. So we've moved along since 1835 when mapping began, going from using pen and paper in the field and staying in some interesting accommodation around the world. to using digital and lots of desk-based analysis that uses data, like I'm sure everybody at USGS is doing as well, and also now more likely drone footage. And now I'm going to pass over to Roxana.
Thank you. So moving from monitoring and data acquisition to maps and models, one of the most important information that we are underpinning, that underpins most of our maps and models, definitely at national and subnational level, is the BGS geology data set. This is a primary data set that actually contains information across different scales from 10,000 to 625,000. And it contains information about the bedrock, the superficial deposits, linear features, artificial material, and as part of this data set, we have mass movements, which of course are important for all our landslide mapping and modeling moving forward.
It's doing it for everyone.
If we mapped geology systematically previously, what we're doing now is to map geology more strategically at local or regional scale. And we use a number of area myriad of techniques that we are continuously developing. And we also transfer and apply this knowledge and expertise internationally. Now, the BGS geology mass movement layer displays mapped landslides that have been recorded by field geologists. And as I mentioned earlier, this is a historical kind of endeavor. Therefore, mass movement layers do not necessarily distinguish between different types of failures, such as rock falls, shallow or translational landslide, debris flows. It is really a data set or an information data that provides an outline of the landslide deposit. So if we look at other types of data sets that are really critical for understanding, modeling, forecasting landslides, superficial thickness is another important one. This one is really a national model that looks at quaternary thickness and rock head elevation. And it is a summary model at 1 kilometer scale, and also provides information about the buried valleys within its surface. It is used to identify proximity to bedrock, superficial aquifers, and groundwater pathways, all of which are really important when it comes down to understanding the spatial probability of debris flows, for example. Another important data set is the BGS soil parent material, which again has a national coverage and is a field scale model looking into the very near surface geology, susceptibility to erosion, soil texture, soil depth, and soil chemistry. It is, again, an input data set for debris flow landslide susceptibility, particularly when it comes down to identifying those type of materials that are susceptible to such processes. But it also has other uses, both in the agricultural sector as a proxy for soil type, as well as for habitat analysis. So if we are looking at how we are actually using these important data layers, one of the key providers of information in terms of modeling of spatial probability of landslides is our suite of geoshore maps, geoshore landslide susceptibility being one of these layers. So we have produced two different types of geoshore landslide susceptibility maps, one for shallow landslides on the left-hand side here, and one for debris flows. We also have other geoshore landslides that landslide layers that we're looking on, but these two are really the ones that we are going to focus also in the next few slides. So such models define areas with similar landslide characteristics at a different scale, and they are informed by landslide evolution, geology, and characteristic landslide processes and drivers. in terms of the input data that these two models contain, the shallow landslides really focuses on shallow translational and rotational landslides, and lithology discontinuities and slope angles are really important in terms of modeling their spatial distribution and probability. And for debris flows, material availability, hydrogeological conditions, and slope angle are important. Now, if we are looking at the methodology behind developing these models, we are using a scoring of different preconditioning factors using basically an expert-based judgment analysis combined with understanding of areas that have been previously affected by landsliding. So, for example, if you look at the debris flow model, availability of the debris material is really taken from the soil parent material map that I showed previously, with consideration given to the ice-scoured domain from the quaternary domain map. So if you look, for example, on the green map, on the right-hand side, you will see that on the western coast of Scotland, the area that has been previously affected by ice scour, you will see a high signal of susceptibility as well. In terms of the hydrological conditions, the geological controls on infiltration, this is a layer that was produced also as part of the suite of information from BGS, and this one gives an indication of how easily water can penetrate into the ground. And finally, the slope and angle and the channel information. So we're looking really at how the terrain, what is the propensity of the terrain to either maintain material or having the possibility of reducing the capacity of the slope to resist gravitational movement. We have looked at susceptibility maps at national scale within Great Britain and UK. We have also done work on landslide susceptibility and hazard internationally, and here I'm just illustrating an example from the UK Space Agency funded Meteor project, where we've worked on landslide susceptibility and hazard, both triggered by rainfall and seismic shocks, so from earthquakes. And this work has been, of course, underpinned by a landslide imagery for both types of triggers. The methodology is really here is developed based on 3 steps. We combined a statistically driven approach with an expert-based validation approach to develop a hybrid model. Initially, we use a frequency ratio distribution to investigate the correlation between landslides and a number of predisposing factors. And then these distributions were used to define rule sets and parameters for a physiologic function associated with each predisposing factor. And the predisposing factor maps were then aggregating using a weighted approach informed by expert ranking. So the hazard maps that you see illustrated here in the lower part of the slide illustrate the distribution of high and very high landslide hazards, both for rainfall and seismic triggered landslides. And for the rainfall triggered landslides, what we observed was that the high and very high landslide hazard is strongly associated with the pattern of extreme 24 hours rainfall over the last 30 years. Whereas for the seismically triggered landslides, the distribution of high and very high landslide hazard is associated with the pattern of peak ground acceleration values with 10% probability of exceedance in 50 years. Moving forward to more localized scales or national scale work, what we are trying to move in terms of modeling is from understanding the hazard, so the spatial and temporal probability or propensity of landslides to their effect on land. So what is the exposure of different critical infrastructure for example, roads and railroads and other types of assets to particular landslide processes, and what is their potential impact. And part of this work, we are using the Scottish Infrastructure Network to carry out an analysis of exposure of roads to debris flows, taking advantage of the knowledge we have about landslide susceptibility and characteristics of roads. For preliminary analysis on exposure, we looked at landslide density, we looked at network density of roads. And in the future, we are interested to look at traffic traffic information and also at road characteristics to improve the information on exposure. The particular interest on roads and networks, of course, is due to the high propensity of the impact that debris flows has on disrupting not only transportation, but also cutting roads and communication between communities. And therefore, it's really important to better understand how such processes can be avoided and how communities can respond better to debris flow events following extreme weather conditions. And as part of this work, we're looking at how best to represent potential impact of debris flows at national scale. And we are using an impact matrix designed to indicate different impact categories for a variety of assets and sectoral categories, from disruption to travel, to danger to life, and damage to buildings. And this is used as a tool for stakeholder communication, preparedness, and response. Now, in terms of forecasts, we do work associated with our BGS susceptibility products, but also as part of an ongoing efforts to improve our local and regional capability to forecast landslides. And one of the main services that we provide is a daily landslide hazard assessment, which is currently based on antecedent soil conditions, precipitation, and landslide susceptibility, as I presented earlier. And this is a service that we provide through the Natural Hazard Partnership, which is a consortium of a number of important organizations, which I will talk about a bit later. Part of the core science that is behind this daily landslide hazard assessment is really to look at how we can better characterize or represent in a standardized way how water moves through the soil. And we do that by looking at different characteristics of the soil within a 1 meter thickness of a soil column. So the water balance model, which is currently being developed by one of our colleagues, Nikhil Vasu, is working on the assumption that the likelihood of landslides being triggered by rainfall is dependent upon the soil moisture conditions of the near surface, in combination with how much rain is forecasted to occur in the following days. So the main focus is really on precipitation-driven events affecting translational instability due to the limitation of the 1 meter thickness in the soil column, and is in the shallow subsurface. So that can potentially, these translational movements can progress into debris flows. The antecedent hydrogeological engineering geological conditions, it's really just a baseline against which we can evaluate the potential effect of forecasted precipitation. And it also contains, in addition to this information through the water balance model, a good understanding of the local conditions and a historical knowledge on how to best marry all these sources of information coming from either the weather forecast, from the soil conditions or the water balance model, as well as a good and expert understanding of the susceptibility models that we have in the house. Another piece of work that is actually, so here in this slide, what we are representing is really how the daily landslide hazard assessment links with the National Hazard Partnership consortium I mentioned earlier. It's really looking at weather-related information through the Hazard Manager platform provided by the Met Office, and combining that, as I said earlier, with our landslide data sets on susceptibility, with a good information about where and when landslides occurred, and these signals are picked up by social media, for example, through the Twitter news events, and then we deliver a bulletin on all this information. And the model antecedent conditions, so the forecasted precipitation, the water balance model, is also provided through the BGS landslide forecasting viewer. Another work that we are currently doing in our team is to try to better understand how we can use our expertise to support the development of early warning systems. And here I'm just illustrating an example of a past project where our team has worked to develop an early warning system for the Geological Survey of India. And part of our work there was to make sure that we use not only highly specialized susceptibility models, data-driven models to assess landslide thresholds, exceedance probability, and develop landslide susceptibility maps and an understanding of the main techniques to develop such maps, but to marry that with our capability to sense landslides either through social medias or different other platforms, and indicate how rainfall forecasting can be used to then develop high-risk weather patterns for landslides on an semi-automatic level through a dashboard platform that can then be used directly by experts to analyze, interpret, and validate those forecasts. Following on the work on forecasting, our team also looks into impact of climate change as an effect of changes in atmospheric conditions and weather patterns. And one project that I would like to highlight here is the Chamfer project, which looks at providing or developing new and essential knowledge on and understanding to determine how multi-hazards at the coast control coastal flooding and erosion, to quantify how these multi-hazards will then respond to climate change and coastal management. The project also looks into providing advice to stakeholders on coastal management and adaptation options. And of course, is trying to understand how different solutions, such as natural-based solutions, perform on coast, and if they have the potential to protect the coast better from the impact of climate change, or compared with traditional engineering solutions, for example, as coastal defenses. Another stream of work that we are developing in terms of the impacts of climate change is our understanding on how the landscape will respond at UK level, and how our resilience, societal resilience, should be taking that into account. The Geoclimate UK CP18 project is really looking at best and worst case scenarios for shrink swell behavior of clay that underlies a significant proportion of densely populated areas in the UK. So this slide's really what it shows is the outputs available for GeoClimate UK CP18 for 2030 and 2070 at the baseline year of 1990. It shows the wetter and the drier projections for these time slices as well, representing a worst and a best scenario. And I've zoomed into the dry 2070 scenario here just to provide some detail about such impacts in the southeastern part of the UK. Part of this work really is trying to look into how GeoClimate UK CP18 provides projections for the high emission scenario for 2030 and 2070 for shrink swell processes. And as you can see in this diagram, this is provided to the GeoIndex platform. And in the next phase, our colleagues will look into focusing on applying these scenarios on UK landslides. And finally, in terms of our work on impacts on climate change, I'm just going to highlight another project that looks into this topic. Terra Firma delivers knowledge on the societal environmental risks associated with overshooting key global warming targets and the feasibility of climate mitigation options. And this is really a collaboration between different NERC centers and the Met Office using CMI E6 data and bespoke UKSM projections. And this work is still ongoing. And we will look particularly in terms of landslide at coastal areas. In terms of the work that looks at integrating different types of hazards and how we can best produce forecasting for different susceptibility to reduce susceptibility to geohazards for different types of stakeholders, we are currently developing at BGS a forecasting platform which aims to produce a range of trusted geohazards under a single platform. We are currently at BGS producing forecasting for groundwater flooding, geomagnetism, and I've mentioned earlier the daily landslide hazard assessment, as well as a groundwater outlook. And our aim is to integrate other types of forecasts into the future for which we are currently providing research, for example, on soil moisture, recharge, seismic hazards, erosion, coastal, as well as fluvial, debris flows, and volcanism. Part of this work is really trying to understand in the first year of this project how we can best work together to achieve a number of objectives which are related with an integrated understanding and of forecasting processes that we can apply in-house. What are the best standards and practices existent? How we can ensure that the products that we put out are quality assured, and we integrate information about validation and uncertainty that is useful for our stakeholders. There are a number of applications for this forecasting platform, one of which, of course, is try to marry that with another strand of work that we do on a dynamic platform, looking at different dynamic processes, both in space and time. Now, moving forward to response, advice, and communication, I'm just going to mention very briefly the work we do with the International Charter. And the fact that BGS is really has provided information very recently to the Charter on landslides after the Turkey-Syria earthquake in February this year. This mainly involved analyzing data and mapping landslides rapidly and reporting this back to the Charter for the stakeholders on the ground for that are involved in the rescue efforts. And in the future, we intend to automate this process and combine it with other ground-based data, such as social media and other types of data in real time. A few words briefly about the work we do in terms of advice for the government, our involvement with local resilience fora and advice for civil protection. So part of the work I presented earlier is related to our role as partners within the Natural Hazard Partnership, which has been established in 2011 following a government review after the 2007 floods. So NHP is a consortium of 19 public bodies which are responsible for coordinating and driving useful, usable, and used scientific advice for governments. And this scientific information, research and analysis on natural hazards is provided to civil contingencies, governments, and UK responder community across the UK. Our contribution into hazard is to provide advice for landslides, earthquakes, tsunamis, and space weather, but we are not mandated to provide warnings for the UK hazards. We are also involved in a number of direct communications with the government, particularly for rapid response and emergency, and also work with local authorities and local resilience forums. But for example, recently we've worked on communicating what is the impact of thermal stress due to heat waves and the potential triggering of rock falls at the coast, as well as advising or on a consultation for the national risk assessment, both on landslides and or more environmental impacts more generally. As part of our work with government and other policy and practice stakeholders, we are also moving towards trying to understand how different risk products or risk information is actually used for policy development and for emergency response as part of those policies and principles that are used in practice. I'm moving slowly towards the end of the presentation, but before that, just a few words about the work we do on social media and the communication on the different streams and on different channels. We are really a publicly funded organization, therefore we have a duty to respond to inquiries from the public, and we provide impartial scientific evidence-based advice, as Kath mentioned at the beginning of the presentation. So social media for us is really important. It's not only a source for near real-time information on landslides, but we really consider it as a two-way communication channel directly, both with people on the ground that are witnessing these processes and their effects, but also the other way around with us and other experts. So this really allows a space for the landslide community to share information, but also reflect on the positives and the limitations of such method. To conclude, we presented an overview of the range of BGS landslide research, which is really interdisciplinary, collaborative, multi-scale, and impact-driven. We talked about the work we do at all spatial scales and temporal as well. And we gave you a few examples of the different technologies which we use to look not only at environmental features, but also to try to understand better what are the impacts of different types of processes on land. And in the table here on the left-hand side, you see, coming back to our discussion on the strategy and the integration of different technologies and techniques, different type of approaches, methods, and technologies that we use either from a geodetic remote sensing perspective or from a geophysical investigation or a geotechnical expert understanding. So joining technologies and data streams is really the approach we use to provide a holistic view on of landslides. And here on this diagram, we just try to capture the wealth of expertise, knowledge, and approaches that we actually need to be able to integrate our expert knowledge with what we actually try to do, which is really increase resilience and reduce risks to landslides. And with this, I thank you for your attention, and we are really open and interested to hear your questions, comments, or remarks. Thank you.